Okay, hello everybody. I'm Neil Roberts. I'm going to be talking about the work we've been doing to add Mediump support to Mesa. So I work for Igalia. So that's just an overview of the slides. So to start with, just a quick recap of what Mediump is. So it's part of GLES. So it's been available in GLES since the first version. And it's a way for an application to tell the driver that a particular operation in a shader can be done with a lower precision than normal. So some hardware can take advantage of this to trade off the precision for speed. So for example, I'm sure you all know that you can have 32-bit floats with which can have a huge range for the float for up to 10 to the 38 and about 7 digits of accuracy. So in some hardware, you can use 16-bit floats as a trade-off. So it can do the operation faster, but you trade off the precision. So you only have about 3 decimal digits of accuracy, and the maximum number you can store is only about 65,000. So in GLES, there are 3 precisions that you can use. So in the spec, each of these precisions has a specific amount of precision that is required to be implemented. So in high P, you need a 16-bit fractional part, so that will usually end up being implemented as a normal single precision 32-bit float. With medium P, you only need a 10-bit fractional part, so that's enough that you could implement it with a half float, 16-bit float. And there's also low P, which is just about enough precision to store an 8-bit color value in the range 0 to 1. Okay, so the precision, it just works like a hint to the driver. So if you declare a variable as medium P, it doesn't affect the actual storage for the variable. So for example, if you have a medium P float in a UBO, that's still going to appear to the application as 32-bit float. So it's really only a hint to the driver to say that the operations using these variables can be done with a lower precision. And these precision requirements are only a minimum. So a valid implementation is actually just to ignore the precision markers and just do everything at high P. And that's what Mesa currently does. So there's 2 ways to specify the precision for a variable. You can just directly add it as a qualifier when you declare the variable. Or the other way is you can declare a global default for each type. So for example, you can say here, all the float types should default to medium P. So if you do that, that includes vector types and matrix types based on floats. So for most of the types, the spec defines a global defaults already, so you can just write the GLES shaders as you would for desktop GL, except that for the floats in a fragment shader, there's no default, and I think that's because in the first version of GLES, the high precision support was optional. So yeah, if you wanted to use high precision, you're supposed to first check whether it was supported before you're using it. So I guess they wanted you to encourage you to specify the precision in your fragment shaders. So when you have an operation in the shader, the precision of the operands to that operation determine the precision that the operation can be done in. So and the precision for the operands sort of escalates a bit like it does in C for the automatic float to double conversion. So here, for example, we have this A times B, and both of these A and B are declared as medium P floats. So this operation can be done in medium P because both operands to the operation are in medium P. So the result of that operation is stored into a high P variable, but that doesn't matter. The operation can still be done in medium P. So there's another example where here we're doing another A times B with the medium P variables. So and then we're multiplying it by another variable. So this inner multiplication, both the operands to this inner multiplication are medium P, so that operation can be done in medium P. But for the outer multiplication, one of the operands is high P, so that multiplication needs to be done in high P. But this is just to highlight that it is the individual operations that the precision determines, so it's not the whole expression. So there's some corner cases, because not everything has a precision. For example, literal float constants, they're not declared with a precision. So in that case, yeah, the precision is just none. But as long as one of the operands to an operation has a precision, that can be used to determine the precision for the operation. So in this example, this pi doesn't have a precision, but the operation can still be done in medium P because at least one of the operands does have a precision. So there's also in a more extreme corner case where none of the operands in an operation have a precision. So in that case, the spec gets a bit more crazy. So in this, yeah, neither operand has a precision. So in this case, according to the spec, you're allowed to look at the precision of values further outside of the tree of the expression. So if you had 3 multiplications together and one of the multiplications didn't have a precision, it could look at the third multiplication for the operands of that to determine the precision. And that goes as far as looking at the L value in an assignment. So as I said before, that the precision of the variable that it's stored in doesn't affect the precision of the operation. But in this corner case, where none of the operands have a precision, the compiler is allowed to look at the precision even of the value that it's stored into to say what precision it could use. So in this case, it would still be allowed to use medium P precision for this multiplication, even though none of the operands have a precision. So what does Mesa currently do with these precision operators? So it doesn't do much. It just passes them and stores them in the IR tree. And as far as I'm aware, they're not really used for anything at the moment except to compare, to check for compile time errors. So for example, if you declare a variable with one precision and you later declare it with another precision, it has enough information to report a compile error. And in desktop GL, in the later versions of DLSL for the desktop GL, the precision qualifiers are allowed to exist in the shader source, but they don't have any bearing. They're supposed to be ignored. So Mesa just immediately sets all the precision on all the variables to none. So normally when the Mesa stores the precision, it stores it in the IR variable. It doesn't form part of the GLSL type. So you might think if you're declaring a medium P float, that might be a medium P float that should form part of the type. But no, it doesn't do that. It's just a float type, and then the variable itself is declared as medium P. But I say, so yeah, that's the precisions that are available in the Mesa tree. So there's the high, medium, low, and none. And yeah, as I say, there's a precision marker stored in the IR variable. So I say it usually doesn't form part of the GSL type, but this gets complicated if you have structs, because in a struct, each member of the struct can be declared with its own precision. So when you declare a struct, the struct becomes a GLSL type, and that type owns the type declarations for each field. And so then in that case, you do have to store the precision in the GLSL type. Yeah, so there's normally there's quite a lot of rules in the spec about what happens when you link together shader interfaces. So if you link between a vertex shader and a fragment shader with medium P in one and float P in the other, it should work. So Mesa has to go through a bit of hoops if you're linking the shader interfaces with a struct, because then you have to try and you normally don't want to take into account the precision, so you just compare the type. But if the type is actually a struct, that type can have precision in it as well. So then you need to specifically, when you compare the types, ignore the precision declarations. So this is what the plan is, to try and take advantage of these Mediump qualifiers in Mesa. So what we want to do is lower these Mediump operations to float 16 types in NER. We want to lower the actual operations instead of the variables. So we don't want to change the type of any variables to be float 16. We just want the actual operations on those variables to be done in float 16. And we need to do this at as high a level as possible because to implement the spec rules correctly, you need to know exactly what the shader looked like in the code. So if you had 3 multiplications in a row, by the time that is translated down to NER, you've probably lost too much information, so you can no longer determine which of those operations was the inner one and which one was the outer one. So you need to do it as high up as possible. So we're doing this work at Igalia. It's myself and Han-Jan. We're doing it with Google. And with the lowering pass was originally inspired by work done by Topi. But we've diverged quite a bit from then, since then. So yeah, it's more inspired by that. So we're trying to specifically get this to work on the Freedreno driver. But the bulk of the work is a lowering pass that could be reused for any driver. Okay. So as an example of how this works, so again, here's an example shader with an operation that can be done at medium precision. Mesa compiles this, so yeah, we only want to lower the operations, not the types. And so the way that we're going to get this to work is whenever we want to lower an operation, we'll add a conversion to float 16 around any dereference to a Mediump variable. And then after the operation is finished, we'll add a conversion back to float 32. So that way, yeah, we're minimizing the modifications to the IR and we're not changing any types. So for this example here, this is the IR that gets generated. So there's 2 variable dereferences there, and those both are used into a division operation. And you can see here this division operation is done with a 32-bit float. So after the lowering pass, so the lowering pass is going to scan through the IR tree and look for any parts of the tree that are only involving Mediump or low P operations. So yeah, when it finds a tree that it thinks it can lower, it goes to the root nodes with the variable dereferences, adds conversions to float 16, and at the end of the tree, it converts it back to float 32. So anything consuming this subsection of the tree can still consider it as float 32. So this is what the IR tree would look like for that example after the pass. So you can see we've got a conversion to float 16 directly after each of the variable dereferences. And then the actual division operation is done with a float 16 type. And then after the division, we convert it back to float 16 before storing it in the output variable. So it's just the operation is lowered. Okay, so this is going to generate a lot of conversion operations in the IR tree, and we obviously don't really want those in the compiled code because, yeah, the idea is to make it faster, not add loads of operations. Yeah, I mentioned that example where it's going to add loads of lowering operations. So here's another example where it's going to be worse. So in this case, we'll lower this first division. So it will add a conversion operation at the end to convert the result of that lowering operation back to float 32 to store it in this variable. And then immediately afterwards, we're going to dereference that variable again and use it in another Mediump operation. So that that dereference is going to add another conversion directly back to float 16 just after having converted it to float 32. So for the NIR that gets generated for that, you can see it makes this monstrosity with lots of redundant conversions to float 32 and back. So obviously we want to get rid of those. So we added a NIR optimization pass that just, whenever there's a conversion between float 32, float 16, and float 32, or the other way around, we just get rid of them. So this is only enabled for GLES because obviously converting to float 16 and back isn't lossless. So if the shader specifically did that, then that would be visible to the application. So what we're doing is we're only enabling this on GLES because in that case the only way you could get to this situation is because of this lowering pass. So it shouldn't be visible to the application if we just remove all these redundant conversions. So I said that in the lowering pass, we don't want to change the types of variables, but in some cases, we actually do want to do that. So yeah, we don't want to change the type of variables, for example, because if we change the type of a uniform, for example, that would be visible to the application outside, because they'd suddenly have to put a float 16 into the buffer instead of a float 32 or whatever, or it might mess up the interstage linking. But in some cases, the hardware can cope with this. So, for example, on Freedreno, the outputs for the fragment shader, they can be half float, and this won't be the type of the output variables from the fragment shader aren't visible to the application anyway, so it doesn't matter if we lower them. So in that last example where I said we convert to float 32 directly before storing in frag color, if we change the type of frag color, we can get rid of this conversion. So we made a pass that's specifically for Freedreno to do this. So it just changes the type for the fragment shader outputs if they're declared as medium P, and in that case, the optimization will end up again with a redundant conversion to float 32 and back, and then finally that NIR pass will get rid of those conversions as well. So this is particularly useful as well because on GLES, all of the built-in variables are declared with a precision, and the fragment color is declared with a medium P by default. So this will help get rid of a conversion by default on a lot of shaders. So just an example of what that lowering pass does. So normally this is that multiplication example in the NIR. It ends up adding that conversion before storing the output. So we can just remove that and then directly store the result from that division operation. So another thing we can do on for this example, in this case, this operation has to be done in high precision because the two variables are declared with high precision. But then because of this lowering pass, the fragment color is going to be converted to 16-bit. So that means we're going to end up with a conversion operation after this high precision division to convert the result back to float 16. So the division will be converted back to float 16 for the output. So in the IR3 disassembly, this will end up looking like this. So this is the division operation, and the two register operands to the division operation are coming from 32-bit registers. And then to store the result, we have this conversion operation back to float 16. But this last conversion it shouldn't be necessary on Arduino because in that case, the destination register is allowed to have a different size from the source registers. So we can fold this last conversion operation directly into the division operation. So we've got a NER pass that does this as well. So this is probably a bit controversial because NER requires that the destination for an instruction has the same bit size as the source operands. So in this case, we're breaking that because we really want, in this case, to have NER operations where the destination bit size is different from the source. So we had to change the NER validation to get this to work. And yeah, this pass is only enabled for Freedreno. Again, just an example showing how that pass works. So this is that same multiplication example, and we've got this last conversion. So we do a multiplication operation with 32 bits, and then we've got a conversion to convert it back to float 16 immediately afterwards. So with this lowering operation, we can remove that final conversion and change the type, change the destination size of the multiplication to 16-bit, even though the source types are still 32-bit. So while we've been developing this, we've obviously been testing it as well, and we're been implementing some piglet tests that use Mediump operations. And most of them, we tried to check that the result of the operation is actually slightly off from what you would expect if it was done at high P. So then we can be pretty confident that at least did something related to lower precision to get the wrong result. So that way, when we make some changes to the pass, if it ends up accidentally disabling the lower precision, then we'll notice the regression. But obviously, these piglet tests, they can't be merged into the piglet master because, yeah, a valid implementation is actually just to do everything at high precision. So it is valid for these tests to fail for that reason. But just in terms of development, it's useful. Okay, so the code for the pass is available on this branch. And we have merge requests to open. So there's 3 merge requests because we've got 1 merge request for the main part of the lowering pass, 1 merge request for the that adds a bunch of Freedreno changes to improve the handling of just float 16 types in general. And I've forgotten what the third one was, but there's a third one. And the tests are available on this branch as well. So that was a lot shorter than it was supposed to be, but there's time for questions.
Pass it to Neil's closer. No, because you're going to need that. This one on? This does not seem like a very good setup. So I've been looking at some similar things for recognizing cases where you have type conversions and being able to fold that into where the ultimate result type doesn't match the types of the sources. For example, I've seen a lot of cases in shaders where they'll do some kind of integer math and then immediately do an int to float conversion, and we can fold those in. And the technique that I've been looking at is while you're doing, instead of doing weird massaging around in NER like this, is just recognizing that pattern of I to F of an integer addition when doing the NER to lower level backend IR conversion and just generating the right kind of instruction there. So you might look at doing something like that instead of making weird stuff like that in NER where you have different bit sizes, because it feels like that might break other things and cause other weird problems.
Yeah, okay.
And then the other suggestion I was going to make is, since you can't merge those tests into Piglet, I mean, that gives some risk of of possible regressions that someone else could introduce. You might think about adding a bunch of unit tests that actually happen at like build time in Mesa I mean, we have a bunch of things like that already that validate that certain lowering passes or optimization passes do the expected things. So adding a bunch more of those seems like a really good fit for this kind of thing.
Okay. Yeah, both seem really good ideas. Yes, thanks. Yeah, I guess for doing it in the IR3 backend, I guess that could make a lot of sense if we don't want to risk breaking there. But yeah, I guess then it's a trade-off as well. If you were just saying, well, this is something that the backends want, and if NER can't do it, then I don't know. Maybe you can say, well, NER should be able to cope with this as well. But if we don't want to change NER, then yeah, doing it in the backend as well could work. Yeah.
Yeah, I mean, so I'm going to try and summarize the discussion that happened when I think this merge request was raised in Mesa a while ago. And the main problem that I had was that, well, yes, it is possible. Like, you can change NER to do whatever you want. But the problem is that it's really a middle-level IR. It's meant to be used by many, many different drivers, and not all of them are going to want this optimization. And it's also meant to do lots of middle-end optimizations that are agnostic about the driver that you're doing, which means that when you make a change like this, you have to update all of the optimizations to be aware of this new fact that you can have different types on the source and destination, and you have to make sure that all of them work with this new pattern, and that they all recognize it, and that they all optimize it the same way that they would with an explicit conversion, and so on. And because what you're changing is so core to how drivers work, like literally every shader has a ton of floating point multiplies and adds, right? And you're changing the behavior of those opcodes that literally everything uses. So it's really difficult to go and change the core IR to support things like that, just because you have to audit all of NER basically, or most of NER, in order to make those kinds of changes. And you're going to wind up masking bugs because someone's going to accidentally have different source and destination types where they didn't mean to, and because you suddenly make this allowed, you're not going to catch those bugs. So I'm kind of with Jason that this is something that falls squarely in your backend needs to have an optimization bucket, because it's just too hard to support something like this in a IR that's meant to be used that's meant to have many different backend independent optimizations and meant to be used by many different backends, and do a competent job at optimizing floating point expressions.
Okay. Yeah, that sounds fair enough. Thanks.
I was going to say the counterpoint to that is, I mean, we can have a compiler option. I said the counterpoint to that, we could have a compiler option flag to say whether the back end allows this or not. That's fine. But the question of to do it in the back end or not, there is a reasonable place in the back end to do it. But the question is, are there any cases where folding the conversion would introduce other opportunities for optimization? And if that's the case, then I'd rather not do it in the back end, because that means pulling more other optimizations into the back end.
Depending on what kind of optimizations, my feeling is probably no. It's not going to be a big extra opportunity to optimize. If you've got a decent CSE pass, for instance, it can just as easily gobble up the conversion and the other opcode as it can just the opcode itself. The other thing that concerns me about it is that even though many instruction set architectures allow for some sort of mixed mode arithmetic, they all do it differently, and they all have a different set of rules and has different semantics. So for instance, the semantics of adding two 32-bit values and storing it in a 16-bit value on Qualcomm hardware might not be the same as on Intel hardware. And so we get into, if we're going to add something like that to Node, we have to define what the semantics are, and we need to be careful and do a fairly thorough audit of the IR and of the hardware available to make sure that we're defining semantics that are consistent and that work for everybody. The other thing is that, at least in our backend, there's a pile of restrictions around what things can accept 16-bit and what kinds of mixed mode operations you can have. And so what we would end up doing in our backend is just splitting it all out into op and conversion and remerging in the backend, because Node just doesn't have enough information. And again, it kind of depends on how the hardware is. If Freedreno's hardware is nice and clean and basically anything can do a 16-bit store from a 32-bit opcode, then maybe we could define a Node level semantic that fits with that. But is it going to fit with anybody else's hardware? That's a good question.
I need to go back and check, but I suspect there's going to be some edge cases. I mean, if you wanted to handle it in NUR, you probably almost need a backend callback. Can this instruction do this combination of things?
Yeah. So in terms of,
And the thing is, you can just leave these conversion opcodes in the NUR and process it in the backend. I do this in V3D all over the place, where I have to look at, when I'm looking at a Boolean source, I have to look and see, oh, is this a comparison operation? And if so, I want to re-emit my comparison and consume the flags directly. I feel like it's normal behavior in your backend to look past a couple of NUR instructions to match a larger tree into a single hardware instruction. I think the lesson from Jason's talk was, when you have one NUR instruction generating multiple backend instructions, you should be looking at pushing that into NUR. But I think leaving NUR in a mode where I can map some larger tree into a single hardware instruction is very reasonable, and kind of how we should be architecting things.
yeah. And something that I was looking at when I was with Booleans is that, for example, very late in the optimization pass, we convert 1-bit Booleans and NUR abstract Booleans into whatever the hardware wants. And there, sometimes there might be additional optimizations that you can do after you lower it. But for every optimization that you do on the lowered form, on the simplified form, you can always write an equivalent optimization on the more explicit form. It just might be a more complicated optimization. So the trade-off is more, do you want to support this lowered form and do optimizations on it? And maybe the optimizations are simpler, but the semantics of the IR are more complex, versus having simpler semantics in the IR, but having maybe a bit more complicated optimizations. And I usually tend towards the latter. I think that that's usually simpler. That's also what we did when we wound up dealing with conversions, and the fact that in NUR at the moment you can't have the same restriction of not having the same source and destination types, meant that there were tons of opcodes for conversions, but it was just easier to make opt-algebraic understand that and make it have a single float to integer instruction that maps to all these different hardware instructions, rather than maps to all these different NUR instructions, rather than having NUR adding this weird corner case to NUR that you then have to go and update all these other places for. So usually it comes out simpler to make the semantics of the IR simpler and the optimizations do more work, rather than the other way around.
Just to add to that a little bit, I think a better example than the conversion opcodes is the fact that Node, for 98% of the time, doesn't have source and destination modifiers. We just have negate, abs, and sat instructions, and we just trust an SSA to be able to gobble everything up. And then for Intel, we have a pass that we use at the end, and I think a couple of the drivers are using it at the very end before we go into the back end. But I've seriously considered just deleting that pass, because I'm not actually convinced that it's worth it versus doing what Eric said and just scan up the tree and look for things. I don't know that we're actually gaining that much from it now. I think we gained something from it earlier on in the new design, when out of SSA was doing more out of SSAing, but now that we have partial SSA, I don't know that we're actually gaining much.
Yeah, I'm still undecided about what the best final thing would be, but I think we start by doing it in the back end. I mean, it's similar to some things we do in the copy propagate pass now. That can be a place to start. I think we'll want to revisit. I mean, maybe solve it with instruction selection or, but I guess that at least gives us flexibility to deal with when we figure out some class of instructions doesn't support, converting or things like that. That gives us more flexibility to deal with that in the short term.
So getting kind of off of the live merge request review, I did actually have another question for Neil. So when Topi and I were talking about this, and we've had several discussions on it while he was working on it, one of the issues we came across was that, at least on Intel hardware, we have certain instructions, texture instructions in particular, that can't consume medium p values. Even if it looks like they can at the GLSL level, we have to insert a conversion. And it's not that inserting the conversion was difficult. The thing that was difficult there was that suddenly we ended up with more conversion operations than ALU operations, and so it turns out that it was better to just not bother with medium p in the first place. Do you have, with this pass, any sort of a strategy for figuring those kinds of things out that, it has to be a hardware-specific way in mitigating the potential fallout from just attempting in kind of a brute force way to do everything medium P, or are you still kind of going with the greedy algorithm and hope for the best?
Yeah, the latter for the moment. But yeah, I guess ideally we think about some way of communicating that back up from the driver to say what operations you can't lower, or yeah, I'm not sure exactly what to do, but yeah, the trick is you have to do it as a high level as possible, and then you need information from the lower level as well. So I guess you have to communicate it back up.
Well, I think part of it is that there are really two parts to it, right? There's, first, I need to, like you said, medium P is really something that's on operations. It's not something that's on variables. So you need to figure out which operations are medium P, right? And then of those medium P operations, you want to figure out which one of those are FP16. And I think what your current pass does is doing both at once, which is fine, like for an initial prototype. It's not a huge problem. But if you want to deal with something like what Jason was talking about, you really need to split those two in half. You need to have some way of communicating all the way down to NIR that this operation is medium P, and maybe we'll lower it to FP16, maybe we won't, right? And then also that allows you to handle SPIR-V, which also has something like medium P, but it's, again, something that's attached to an operation. It's like a modifier that applies to a multiply or an add or something that tells you that this multiply can be done in medium P.
Yeah, I think perhaps that would be the ideal situation, as you're saying, yeah, just generate the NIR and somehow mark in the NIR whether, for each operation, whether this was marked as lower precision in the GLSL or not. But yeah, I guess that's going to be quite a lot of work to try and maintain those markers after all the transformations and optimizations that are done in there. But, yeah.
I mean, maybe what it occurred to me, it sounds a lot like what Connor's just describing sounds an awful lot like the way we handle precise today, right? Is that it's a thing it's an attribute of the operation, and we track it through all the operations all the way through, and it's just an extra bit. And yeah, all the optimizations kind of have to be aware of that, but we've kind of already gone down that path, right, with precise. So it seems like a lot of that same kind of mechanism could just be reproduced again for this, and it wouldn't be too foreign or weird.
Right. So that's definitely one way to solve it. The main problem when I thought of this was that when I thought of like, well, how the heck are we going to pass this marker down? Like you said, The problem is that algebraic optimizations, it's a lot harder to deal with because, so for precise, it's actually pretty easy. We just mark optimizations as being precise or not. And if they're precise, then you can't have anything, any precise things on the left-hand side. And if there's anything imprecise on the left-hand side, then the entire right-hand side is precise. Or sorry, if there's anything imprecise on the left-hand side, the entire right-hand side is imprecise automatically. But it's not as clear for medium P. If like you match something and half of the things are marked medium P and half of them on the left-hand side aren't, which things on the right-hand side should get marked as medium P and which ones shouldn't, right? So we have a type system, right? We have this notion of bit sizes in algebraic, which like is something, again, it's something very similar, right? Where you need to figure out what the size, given the types on the left-hand side, what the types on the right-hand side should be. So my suggestion would be to think about leveraging that instead of using a model similar to precise, because it's much closer to what you actually want. So even if there's like an even if it's a mark on the operation, maybe in opt-algebraic, you think of it as a type, similar to like 16 or 32-bit. Or you explicitly make it a type in NIR, but then you need extra conversions because it's supposed to be something that's on operations, but then making it a type means that it's now a property of SSA values, which means that if you have like a medium P thing that feeds into a not medium P thing, now you need a conversion, even though it's like not really necessary, right? You've not decided which things are FP16. You shouldn't need to insert conversions, but if you go that route of making it like a 24-bit type or something, then you do need to insert those. So there are definitely different trade-offs, and it's not something that's you can do right away. It's not something there's an obvious right way to do it.
Yeah, at one point in time, we did consider 24-bit types for medium P as kind of the marker. And like Connor said, it kind of has a whole other set of issues because suddenly you have conversions all over the place, and then you have to have a lowering pass fairly late, which actually lowers things to 32 or 64-bit based off of probably some compiler callback function or something. I am less convinced than Connor that Ian's suggestion of treating it like exact would not work. I think it might be able to work, but the big thing is figuring out how to do it properly in opt-algebraic, because the way it works for exact today is that exact is contagious, where the moment you do some optimizations are declared inexact, in which case they will not trigger if anything on the right-hand side is exact, and anytime we do an algebraic optimization where anything in the right-hand side is exact, we declare the entire replacement expression exact. And it works, but it tends to make things infectious. And so if we did that same thing with medium P, 32-bit would be the thing that would be infectious, and it could end up destroying a lot of medium P, potentially. But without actually throwing some shaders at it and seeing what happens, it's kind of hard to know for sure how bad it would end up being. It could be just fine, or it could be the death of that particular engineering solution.
So I just want to throw a nasty wrench into this whole thing, because I have some hardware that I'm working on a prototype driver for, the Tegra 3 by NVIDIA, and that is a little bit nastier. The medium P is not 16-bit. It's a weird custom 24-bit floating point format. So it's it's pretty nasty. And I just wonder, for there, like the whole idea of encoding this as just a bit size on floating point doesn't really work there. At least you kind of have to like overload the meaning of that somehow nastily. Would it make sense to do something like weird instead, like adding, like instead of having a size, having a size and a minimum size, or on the types, so you can like kind of track what what the least operation you need for an output?
Yeah, and like I said, there is a ton of machinery in algebraic, which Jason and I have both worked on, which is all about types, right? It's all about figuring out, like, okay, there are a bunch of operations in NER that are obviously agnostic on bit size, and so they work on every different bit size. But it's really just a type. It's just the fact that right now, the only types are based on how many bits there are. There's nothing more to it, as there's like just a 32-bit type in NER, and a 16-bit type, and a 1-bit type. There's nothing more sophisticated than that. So you definitely could go into all the places that deal with bit size and change it to make it a proper type, where it's like a medium P 32-bit thing or whatever. But yeah, it's, as you can hear from Jason, it would be a lot of work.
Yeah, just to add to that, I guess just in defense of the pass, if it's we can it's currently just well, it's currently on a branch, and it's currently only enabled with a debug option. So at least I think it could be something to get us started. And yeah, because the pass is just in a standalone corner, so it's easy to rip back out again if we decide we want to do it another way later.
Yeah, I do think that doing the pass, at least the sort of information gathering pass, at the GLS-LIO level is the right place to do it, possibly even before any optimizations have happened there, depending on how much data those optimizations destroy. I don't have a good feel for that. Then there's a sort of a separable problem of communicating that information down to some level at which point actual types are assigned. And that second part is the part that's a lot less clear where it needs to be. And I think that if there's one thing that we can take away from this kind of sudden roundtable, it's that the engineering solution here is not obvious. And we're going to have to experiment, and that means probably implementing it at several different levels and just seeing which one actually works out best. And so, yeah, all that is to say, not trying to be critical of the work that's happened. Like, I know, working with Topi on this, I know Topi implemented it at least 2 levels, probably 3, and I don't think he liked any of them. So, yeah, there's lots of work to be done here, and I'm very appreciative that you guys are taking it on. It's something that we need to do. You know, we typically at Intel haven't bothered with it much, partly because we do have a lot of stuff that has to be bumped to FP32, and so it's more questionable how useful it is, and partly just because ALU bandwidth, ALU throughput doesn't tend to be a bottleneck, but there's definitely cases. It's definitely useful, especially for a lot of the mobile people, and I think it would be useful for us if we could figure out how to do it properly. So just thank you very much for working on it. It's very appreciated. Don't want all the sudden discussion to get anybody down.
Thanks.
So would a way forward for this be to land the GLSL information gathering pass, and then maybe we could experiment with the NER-specific lowering and rewrites in Freedreno, and we could then, when a second backend comes along and says we want FP16.2, they could copy from that, or they could go down their own path, and then maybe down the road we'll figure out what the right solution is. But if we want to move forward with this, we could we land the GLSL part and then.
Sure. The one thing that I think that there's serious concern about landing is the changes to validation to allow mixed mode instructions. As long as you can do something where you insert a multiply that's immediately consumed by a conversion, and you're able to scrape that up in the back end and turn it into a mixed mode instruction, then I think that landing what is there and iterating on it is perfectly reasonable. The only thing that's concerning to people is the mixed mode instruction thing.
Yeah, and I think that would be fair to take that out for now and just keep NER with the same bit sizes on both sides of operations. And I don't think anybody here has been able to come up with a concrete example where doing it in the backend actually obstructs ALU optimizations. So I think might be useful to do, and if we encounter something, we'll know what it is when we hit it, and we can take it from there.
The number one thing we need is data. And the easiest way to get data is to get it landed and get people using it. And as we gain experience with it, it will get better. It's just not clear what the future is. So, let's not make major surgical no changes for a future that we don't know is going to be correct. But yeah, I'm happy to land a partial solution as long as it's not a regression somewhere.
Yeah, so I think in the beginning, I objected a little to it being on GLSL-IR, but the reason for that was the stuff that you were talking about, where the precision has to be propagated up and down the tree, and the fact that when you translate to GLSL-IR, you oftentimes have to split the tree in half, right? Which makes it a lot more complicated. It seems like you have enough of a solution that it should work most of the time, so it's not a huge deal. And the thing that, for example, GLSL does, which is what I think, and because John wrote the spec and wrote GLS lang, it's probably what he meant for it to do, is for you to do type analysis first, propagate types, and then do the medium P analysis, and then generate code, right? But I think the problem was that the type in Mesa, the type analysis and the generating code part happen at the same time, which means that you can't do the medium P analysis in between. So I think it's fine to do it in GLSL for now if it works in like 99% of the time. Just make sure that you actually do it as early as possible, because as soon as you start doing things like tree grafting and other optimizations, that messes around with it.
Yeah, I guess the main thing is to not do a lowering when we shouldn't. And as far as I'm aware, so far we haven't come across any cases where the lowering pass would do a lowering where it's not allowed. But yeah, I guess there are cases where if we do the analysis a bit earlier or with more information, then we could do the lowering more often. But I guess on the other hand as well, if those cases where that's useful is only really where it's in those situations where both operands to an operation don't have a precision. I really struggled to try and think of an actual example where that, and I ended up with that ridiculous example where it's converting a Boolean to a float. I mean, I guess if that's the only corner cases where we're not going to hit, like, who cares really?
Yeah. So I think. I heard somebody mention that we're like 10 minutes past time. So I think that this sounds like a good topic for a potential breakout sometime tomorrow or Friday, because most of the compiler talks are today. So maybe we should plan to continue the discussion then, and we can all thank Neil and move on to the next talk.